Okay, so let's go ahead and prove the derivative of tangent x today. Okay. So the claim here is that if f of x is equal to tangent of x, f prime of x is equal to secant squared x. Okay. All right, let's prove it. And using, of course, the definition of the derivative as a limit. That's the way we do it around here. Okay, so f prime of x is, of course, by definition equal to the limit as h trends to 0 of tangent of x plus h, okay, minus the tangent of x all over h. Okay. Okay, well, I am going to be using the tangent of a sum property. I will put that in the box over here. Let's maybe zoom out one step. So we know that the tangent of the quantity a plus or minus b, okay, is equal to tangent of a plus or minus the tangent of b, all divided by 1 minus or plus tangent of a times the tangent of b. And for the proof of this statement, you can refer to my other video in which I prove this. Okay. All right. So clearly this is going to come in handy here. Okay, we've got the tangent of a sum. So let's go ahead and apply this formula. Here we're going to have this going to be equal to the limit as h trends to 0. Okay, we're going to have tangent of x plus tangent of h, okay, over 1 minus tan x tan h, okay, all of that minus tan x, and then of course all of that multiplied by 1 over h, right? Just multiplying by the reciprocal. Okay. Pretty straightforward so far. Just checking our work, making sure we haven't committed any careless mistakes. Looks clean. All right. So let's get this into a nice compact fraction, right? One numerator over one denominator. That means I'm going to have to multiply top and bottom over here by 1 minus tan x tan h. So here we go. We're going to have the limit as h trends to 0. Okay, it's going to be tan x plus tan h, okay, minus tan x times the quantity 1 minus tan x tan h, right? Common denominator. I'm not brave enough to make this line straight, so I'm going to cheat. There we go. And of course, we're going to have an h here. Let's not forget about that. But we're also going to have now this common denominator factor 1 minus tan x tan h. So let's make sure we get that in there, just like so. Okay, well, let's take a close look at what we have and make sure that we've committed no careless errors. Looking good. Yeah, I don't see any careless errors there. Let's now use the distributive property here. This is going to give us the limit as h trends to 0. And we got up here tan x plus tan h, okay, minus tan x. Ooh, that's convenient. Okay, minus a negative, so plus tangent squared tan h. Okay, tangent squared x, I should say, tan h. Okay, and that's, of course, all going to be divided by h times the quantity, of course, 1 minus tan x tan h. All righty. Let's check to make sure we've committed no careless mistakes. Looking good, okay. So tan x minus tan x, of course, is going to go to 0. That was nice. And this term here and this term here have a tan h in common. Let's go ahead and take a tan h out. So this is going to give us the limit as h trends to 0. We're going to have now tan h, okay, and then in parentheses, 1 plus tangent squared x, okay, 1 plus tangent squared x, okay, all of that divided by h times, of course, the quantity 1 minus tan x, tan h. All right. Well, 1 plus tangent squared x is equal to secant squared x, right? And this has, of course, been proven in another video, so feel free to refer to that proof if you so desire. Put that in the box there. This is a property that, or rather, an identity that we're going to be using. So it's going to give us here the limit as h trends to 0 of tan h secant squared x over h, and then of course 1 minus tan x tan h. Okay. All right, let's check that. Yep, looking good. Now keep in mind this limit is dependent on h, it's not dependent on x. So I can take this whole thing out. I don't even need to worry about that thing. That's nice. That's very nice. Okay, so let's do that. We're going to have secant squared x, that comes out, multiplied by the limit as h trends to 0 of tan h over h times 1 over, you'll see in a second why I'm doing this, 1 minus tan x tan h. Okay. Okay. Now, we know that the limit of a product is the same thing as the product of limits. Okay. So that's one thing I want to make sure we establish here. That's a very important property of limits. And the limit properties are exactly as we would want them to be, right? I mean, the limit of a sum of limits, limit of a difference is a difference of limits, limit of a quotient of limits, limit of a function is a function of a limit of the function. I mean, it's everything we would want it to be. And perhaps in a future video, I will demonstrate using real analysis or using arguments from real analysis why the limit properties are what they are, why they're so convenient. But that's not for this video. If the viewer is seeking to prove the derivative of tan, I'm assuming, hopefully correctly, that the viewer is comfortable with these statements right here. Okay, so that's going to allow me to write this as secant squared x times the limit as h trends to 0 of tan h over h times the limit as h trends to 0 of 1 over 1 minus tan x tan h. Okay, just like that. All right, let's zoom out one step there. Now, the limit as h goes to 0 of this is just 1. Tangent of 0 is 0. We can use direct substitution here, okay? Even though the limit's not concerned with what happens at, but what happens near, if the limit so happens to be defined at, then we can plug it in, and we can. So tangent of 0 is 0, and so it's 1 over 1 minus 0, which is 1 over 1, which is 1. This, I'm going to show you, is going to be 1. I'm going to use a diagrammatical argument here to show that. Okay. It's important that the viewer sees these arguments if the viewer has not seen them yet. So this would be, we're going to call this, well, let's go ahead and call this one here, we're going to call this here y1 equals h. And we're going to call this y2 is equal to tangent of h. All right, now what's happening right here? Okay. We know by L'Hopital's rule, okay, that if you have an indeterminate form of the type 0 over 0 or plus or minus infinity over plus or minus infinity, as we do here, 0 over 0, you can just take the derivative of the top, take the derivative of the bottom, and there you go. Evaluate the limit. Okay, as h goes to 0, okay, both y1 and y2 also approach 0. Okay. And moreover, at a rate of, maybe zoom out one more step, at a rate of ddh, okay, is equal to 1. All right. So if you were to zoom in on this, okay, you would find that the graph of tangent of h and the graph of h are virtually indistinguishable. Okay. And because the limit is not concerned with what happens at, but what happens near, I can let h get as close to 0 as I want, and I know that the ratio of y1 over y2, the limit as h goes to 0 of that is going to be 1. Okay, so as h goes to 0, both y1 and y2 approach 0 at a rate of ddh equals 1. Instantaneous rate of change is going to be 1. Okay, hence, okay, the limit, okay, as h goes to 0 of y1 over y2 equals 1. Okay, there you go. And there is a proof of L'Hopital's rule up on the channel, so feel free to access that. Okay, the proof of that is not so bad. Okay, we're done here. This is going to be secant squared x, okay, times 1 times 1, and there you go. All right. Hopefully you found that this video to be educational. Now, hopefully, you understand not only how the derivative of tangent x is equal to secant squared x, but why the derivative of tangent x is equal to secant squared x. We always appreciate your comments, questions, concerns, and welcome any recommendations for future content. Have a great rest of your day, and we will see you in the next video.